look at. Might have to break this up into 2 lessons. Okay, so we've seen that a moving charge in a magnetic field will experience a force. Do you remember what the formula is?
Yeah.
You do.
Yeah.
That's for a current. What about just a point charge, QVB, yeah, or BIL if it's a current. Okay, so what happens if we move the magnetic field? So let's say in the previous lesson we have the magnetic field which doesn't move, and then we have a charge that we move, and there's a force on it, QVB. But now we'll do something a little different. This time we have a conductor and we move the magnetic field. And in fact, what happens in that situation when we move the magnet, we actually make a current.
Come on. Oh.
We actually make a current show up in the conductor. So we can actually cause the current to appear in the conductor simply by just taking a magnet and moving it over the conductor. This is actually called electromagnetic induction. As a very simple experiment to show this, you just pass the magnet in and out around this conductor, and we can see a voltage appear. What do you think would affect the voltage here with the magnetic field? Well, if it's a stronger magnet, then we should get
change.
Yeah. But really what is most important we'll see is how quickly we change the magnetic field. So if we move this really fast, we can actually get a higher voltage. I think it's good if you can draw this, because it's a very simple way to show this electromagnetic induction. Draw this, it's simple, draw this.
3D or 2D?
A little 3D.
What is electricity?
Okay, did you draw that? Oh, whose essay had the safe firing angle? Was that you, Bruce? Your physics essay, the one that had the safe firing angle.
Safe firing angle? What? Safe firing angle? What is safe?
Somebody didn't get. I don't have a cover sheet for somebody. Huh? I don't know if it's yours actually. I don't think it is. It's I think it's someone else's.
What's this?
The first section was about safe firing angle.
Okay, not mine.
I think it's you. Yeah. You can just email me a cover sheet. Cover sheet. You know the cover sheet? You do. You know, you put on the front of your assignment and you sign it.
The one, the page.
You know this page? Yeah, I need one.
From the area.
Yeah, for the physics. Huh?
Just for the physics.
Just for the physics. Yeah. All right, you drew this?
I sent to you.
You can email.
How to email?
Fill it out.
I take picture.
A good picture. Yeah. All right. Continue. So, the precise definition is electromagnetic induction is the production of a voltage across the conductor when you use a time varying magnetic field. Okay, you need this definition.
It's confusing.
Is it? What part's confusing?
Across a conductor exposed to a time varying magnetic field, I think.
Okay, electromagnetic induction is. That's okay.
Yeah.
The production of a EMF, a voltage.
It's okay.
Yeah. Across, so that means over, a conductor by using a changing magnetic field that changes over time.
Mm.
Yeah?
Okay.
Okay.
Do you have to write a time thing?
Yeah. You really, really just want to reduce your definition by one word.
No, like exposed to a very magnetic field. Time makes it confusing.
Yes, you can.
What do you mean by electromagnetic?
That's an EMF. That's another name for a voltage. Do you remember in the electricity chapter we have EMFs?
Yeah.
What's wrong? What's wrong?
I'm going to throw the hair.
You want to what?
Throw the hair.
Throw the hair?
Fake hair.
Whose hair is that?
Joyce.
Whose?
Joy.
And why do you have Joy's hair?
Fake hair.
She cut.
Still, why do you have her fake hair?
I was playing with it just now.
But why are you playing with Joy's fake hair?
Because it's fun and I've played stuff like that before.
Do you normally play with students' hair?
This is the first time there's fake hair.
You were playing with her hair and it fell out.
No. It fell out. So I played it.
So somebody's hair falls out and you think, I'm going to play with that.
It's a fake. Have you seen hair like this before?
Yeah, that's not the problem. My problem is why you would think, oh look, her hair fell out. I'll take that. Okay, whatever. Strange. Okay, that is, induction means producing a current by changing a magnetic field. So we have two laws regarding this. So the first one is called Lenz's law. Does anybody know Lenz's law for this topic? Have you studied it before?
Lenz.
What is it, Shama, if you know it?
I know.
Ah, go on, tell us then. What is it?
I don't know.
Ah, then you don't know it.
Lenz.
I do.
Lenz.
It's actually, no, not this Lenz, no.
They will.
When you
Yeah?
move the magnetic,
Yeah?
Something happen.
you will reduce.
Yeah?
That's the, I cannot remember.
Nah. Yeah, okay, so Lenz's law said if an induced current flows, its direction is always such that it will oppose the change which produced it. So let me explain that with a picture here. So this is Lenz's law, okay? So you see in this picture here, you're moving the magnetic field is from north to south, okay? But the magnetic field, you move it in here. So it's as it moves into the coil, the current moves back out the other side. So you can see the current comes out here. It comes out the part the magnet's going in. And here, if you move the magnet out, so it's coming out here, then the current will go in, go to the right. So here, the current is actually going to the left as the magnet goes to the right. And here, if you move the magnet back out to the left, then the current goes into the right. This is Lenz's law. Yeah?
But that happens even though the magnetic field doesn't change at all.
Say again?
The electric field
it changes direction, although the magnetic field doesn't?
Yeah, I get what you're saying because it's still north-south, north-south. What actually changing here is, although it's the same magnet, here it's moving to the right and here it's moving to the left. And that's enough to cause the current to flip around. So here, as it moves to the right, the current is going to the left. And here, as it moves back out to the left, the current now is going to the right. It's heading in the coil to the right. Yeah. Yeah?
If the magnetic is in here.
If it's in here.
Yeah.
Yeah.
Inside the coil. What is this? Is S or N? End of the coil.
I'm confused. What do you mean?
You know,
No.
this is magnetic. Magnetic.
Yeah.
And this is S. This is coil.
Yeah.
Boom, 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 boom.
Yeah.
This is N now. What do you mean there? Like,
I'm not sure what the purpose of having the S and the N here is. You mean the is? Good question.
I think when we move this it will change the magnet.
Yeah. I think what they're saying here, you remember that if you have a current, by using the right-hand rule, you have a magnetic field.
right-hander?
Yeah, the right-hand grip rule.
Yeah.
So we also remember that if you have a solenoid, do you remember a solenoid?
Mm-hmm.
It's a magnet that has a current around it. So I think what they're saying here is, when this is moving in, it makes a current, and the current makes a solenoid, and the solenoid becomes a magnet, and it will look like a magnet who has a north here and a south here. And here, as you move the magnet out, you'll make a current. The current will make this a solenoid. The solenoid will behave like a magnet who has a south here and a north here. But that's not part of Lenz's law. Lenz's law is just, if this is going in, then the current is going out. And if this is coming out, the current's going in. That's Lenz's law.
That's it?
That's it. The induced current flows, its direction is always such that it will oppose the change which produced it. So it's you know the word oppose? Means like push against. So here the magnet is coming in, so it's like the current is pushing out. Do you understand? And here the magnet is leaving, so it's like the current is pulling in. Yeah. That's what this oppose means. Acting opposite. Do we get this okay? Or not? You don't look too happy with this.
If we don't have a magnetic bar,
Yeah.
then the current is still flow.
Oh no! No magnet, no current.
Okay. Okay, then the distance should be closed. The distance between them should be closed.
Yeah.
And then enough close, the current is start to flow.
Yeah.
And then this end of this coil should be N4.
Here?
Yeah.
Yeah.
Boom, 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 boom. N4. If this magnetic bar is leave to this from this,
Yeah.
and this is.
Then it becomes south. Question? Please ask.
One question.
Try. What are you unhappy about here?
We learned it differently in high school.
What did you learn?
When it opposes, means like the polarity is opposing.
Oh yeah, so like you mean the magnet here?
Yeah.
Yeah, well you can see that's true for this picture. Because this north is coming in, and then there's like, this is opposite to this. So you're happy with this? Yeah. And you are happy or not happy with this picture? Because it kind of looks like it's not opposing, doesn't it?
It is
Okay, so you're happy with this then, okay. So then what are you not happy with? Just that in high school you learned it differently.
You said that the current is pushing outwards.
Well, you can see in the picture here the current's coming down, yeah? So, it's because the current is moving from here. The current, we agree the current's going to the left. And here the magnet's going to the right. So that's opposed. Okay, so...
I think
like how you explained it.
Oh, that's fine. That's fine. That's fine. You have a different way to state the law. Or you just don't like me personally. So...
Both.
Or both. Yeah, so what way did you have it in high school then?
No, the definition is the same.
the fish is same, but the
So it's just me then. It's all me then. Yeah. Let's turn this back on. The reason. Okay. The reason I'm not talking about the polarity so much, there's a reason for that, is because I said we have two laws to do. Okay. The second law actually includes Lenz law in it, but it includes it as a sign, as a plus minus, as part of a formula. In other words, for me, what's important about Lenz's law is the current here, if it's a plus or if it's a minus. So for example, in this picture here, if I call right positive and left negative, here the magnetic field is moving positive, and the current here is negative. And here the magnet is exiting, it's leaving, so its change is negative, it's heading to the left, whereas here the current is positive. It's this that's important for the next law. Yeah. And then, well, I'm trying to get to it, yeah. So anyways, can you write Lenz's law down, please? Or we have it?
can I understand like this?
I don't know if you can understand. Go on, what?
I mean just like this picture is like they like they want to keep the properly relationship.
What do you mean?
Like the first picture,
Yeah?
the magnet is close to the coil.
Yeah?
Coil doesn't want
it, yeah.
too close.
Yeah.
But the second picture, the magnet leaves from the coil to another way.
So it wants it.
Yeah, wants to, but the not close the properly relationship. Like that's enough. Like is this point? Okay, that's enough. Too close is not enough. Like this.
Yeah, okay,
Okay.
that's fine.
Is it okay?
It's fine. Yeah, that's interesting. That's very interesting way of thinking about it, yeah.
It's okay.
I'd like to move on, but my teacher spider senses are telling me you're not happy with this.
Why do you say the current moves to the left
So,
in the left picture?
isn't it moving to the left though? Well, it's coming out here.
Yeah.
This is down, so it's moving to the left. Like it starts its life here, and it moves its way to the left and comes out here. No,
Because this wrong.
Coil?
it moves leftwards in the coil.
This wrong.
But the meter is pushing to the right.
The what is? But that's only. Yeah, but that's only. But I mean, that's just a measuring device. Like if I was to just turn this around, it'd be pointing to the left. Like it's what's happening here that's important. This is just to detect the current. Like obviously you're right, it's moving to the right here, but this is where the action is. This is just a measuring device. It's not a. You're unhappy that this is pointing right when I'm saying left. But when I say left, I'm talking about in the coil, because this is where the current is induced. This is where the current is created, induced. What can I do to make it better?
Move on.
Move on? Okay. Right. So the next one. So far we know a moving magnetic field will cause a current to flow in a conductor. And we know the direction of the current is to oppose the field. But we do not know how to calculate the voltage. So, I mean, this is great and all, but we actually don't know how much voltage there will be. But there's actually a law to calculate the voltage discovered by Faraday. And Faraday's law lets us calculate how much voltage we have. Now, Faraday's law has two parts to it. So, the minus, the only reason the minus is here is actually, this is Lenz's law, that the minus is to remind us that the voltage is in the opposite direction to the change in the magnetic flux. That's the only reason the minus is there. In fact, you can drop the minus if you only want to calculate the voltage, you don't care about the direction. What do you think the n represents here?
Time?
Number of loops, yeah. Which is, if we think about it, this is like the flux linkage we were talking about last time. Remember the flux linkage?
Yeah.
This on the top, the flux. But precisely what is this? The change in the flux per change in time. And the minus, in fact, is Lenz's law. Okay, so if you can write down Faraday's law.
Is there proof?
A proof?
Yeah, for this.
Of course. Do I know it? No.
You can try
Oh no, I
to
couldn't.
find the proof.
No.
No, it's hard.
And yeah. I think prove it by experiment. Yeah?
Natural definition.
Hmm?
Natural definition.
This is a formula, Faraday's law. Faraday's law lets you calculate the voltage.
Is there a word? The minus is
You don't. Faraday's law.
at least.
Well, you know what all the letters stand for, don't you?
What is the time?
Yeah, of course. Yeah.
Faraday. Friday.
I'm sorry, I didn't write down what the letters are because we just did it yesterday.
Like Lenz for the definition. And the explanation.
OMG.
No, just ask.
Okay. No, you're right. If you want to put it into words, you can say
I don't.
the EMF is equal to the change in flux per unit time. No, sorry, excuse me. Change in flux linkage per unit time.
Oh, it's linkage.
So you then we just write the formula down, right?
Let me write it down for you. You can write down the formula and explain all the letters. Okay.
So much for warning.
No, they just want words. The induced EMF is equal to the rate of change in flux linkage per unit time across. Oh no, that's enough.
Also.
Huh? No, see, by using the word flux linkage, I've included the number of loops because linkage means total.
Yeah, you have to say also the minus is impact provided by Lenz.
I don't.
If you want,
Because that's
you can
Lenz's law.
drop down.
So you can just write plus Lenz's law. Ha, ha, ha. Alright, do you have Faraday's law now?
I'm gonna write it down.
Is it just for Audrey?
I was just asking out of curiosity, but then you provide it.
Continue? Yep.
Yeah.
No. See, now look, you're making poor Wookie write this down now.
I think this is good.
You do? Oh yeah, okay, yeah, you're right, yeah.
This is good, I think. It makes me more the understanding.
Okay.
I need to do this for you.
Yes.
Plus then this one.
When do we need hand iron like?
Which one? The essay?
No, that report.
Oh, we have to finish preparing it in class. So we still have.
I'm gonna check like, can we do a draft?
If you want, you can email me your draft. Yeah. All right, continue.
You can email me.
Yeah, send your draft to Wiki, thanks. Right. So, if we move a magnetic field around a conductor, or a conductor around the field, then can we use this to generate power? So, obviously, okay, imagine this is the conductor, and this is the magnet, and if I move the magnet around the conductor, I make a voltage here. But you understand, of course, that's the same as not moving the magnet, but moving the conductor. I mean, it's the same thing. So, could you do this to make electricity? And the answer is yes. This is how they make electricity in power plants. Okay? So we're going to have a look at what's called the AC generator. Very, very important modern technology. Now, it's a little bit hard to see. Let me just explain it here. It looks a lot like
DC
the
motor.
DC motor, except there's actually a small difference. Something to do with the connection.
The brush.
The brush is different. How?
Different position. And
Yeah.
they are separated.
The separate, yeah. So you remember in the DC motor, it was one ring that was broken in two halves.
Yeah.
Whereas here, you actually have two complete rings. Now this is actually necessary for how it works. You actually need two rings instead of one ring. But you get the same idea. Okay, so this is a conductor, and somebody turns this wheel. So they turn the wheel. And this turning around is like if somebody took the magnet and turned the magnet around. So what do you get here? You get a current. And positive comes out here, negative goes in here, and you can use this to power a resistor. And then you have, if you have a bicycle, you might have one of these on your bicycle. Because when you turn the light on your bicycle, as you cycle, you're making the power for the light on the bicycle. Do you know the little light on the bicycle? No? It works off of this. Yeah. So as you cycle the bike, you're turning this little wheel, and it makes electricity, and it lights up the little LED light on the front of the bicycle. Same thing as in a car. You know, when you drive your car around, it charges the battery up the same way like this. Power plant uses this. So how do they make the wheel turn at a power plant? Well, if it's a wind power plant, it's just the wind. If it's beside a waterfall, they use the water to turn the wheel. Yeah. Huh? The turbines. Yeah, the big turbines for turning. Very important piece of technology. And again, also very old. You know, like, this is maybe over 100 years old. Yeah. Yeah. These are called slip rings, and again, you could use a carbon brush. What do you think?
Draw again.
Yeah. Now, before you draw, talk a little bit about the voltage here. So you remember we have voltage equals the change in the flux linkage. Now, what is the formula for the flux? That's BA.
Yeah.
Yeah? So we can change this formula into change in BA over T. And I'm going to forget about the minus N. I don't care about that right now. Just forget about it for the moment. Okay. Now, how does the BA change? Like, we actually know why or how it's changing. Because remember, we had the formula flux equals BA. But that's if it's perpendicular. If it's at an angle, then we have the formula BA cos theta. So actually, because the angle is changing, it's actually we need to consider the theta. So we have to add a cos theta. So now we have this formula, BA cos theta, instead of BA. But how does BA cos theta change? Well, this is like me asking you what's the derivative of cos. What is the derivative of cos?
Sine.
Sine. So the BA is constant, so really how does the cos change? Well, that's sine from maths class. So before you draw it, this is what the voltage will look like. When it starts vertically, we have no voltage, and then we start to rotate it. When it's at 90, so it rotates 90, that's when we get most voltage. But then the voltage starts to decrease, so it starts vertically, rotates 90, and then when it gets to 180, we have no voltage. And then when it gets to 270, what's happened here, the current has changed directions. So maybe the current was going this way, and then now it's heading the other way. In fact, that's why we call it AC. Does anyone know what the A stands for?
Yeah.
Alternate. So alternate means change in directions. Okay. So here the current is coming left to right, but then when this flips around, the current will be going right to left. So the current keeps changing its direction, and it gets strong, weak, left, right, left, strong, weak, keeps changing its direction. So what I need you to draw is this, please. Yes.
So what is the formula?
For
Sine of cos.
AC.
oh no, this here. The only reason I have this here is I want to explain this graph is like a sine graph. In fact, it is a sine graph. So what I'm trying to say is, if you were to plot the voltage, you'll get the exact same graph as a sine graph. And I'm trying to give you the reason why. Now you don't. Oh, in the exam they don't care about if you know the reason why. In the exam they sometimes ask students to draw this graph. So you need this graph, and you also need this picture here.
And there is space between the rings.
Yeah, they're separate a little distance, but they're complete rings. There's no gap in the ring. Do you need me to zoom in on this?
There's that exhaust in there. Like the current flow in both of them.
I'll try and draw it a bit zoomed in. Oh, you know what? Actually, I'll zoom in for you.
View.
Can you see it? So there's a current. The current is coming out of this ring. There's a wire that passes through the first ring but connects with the second ring. These are not touching. There's one connection here onto this side and one connection here onto this side. And these rings don't touch. And the current comes out of the first one, has to travel all the way around before it can enter into the other one. Is it up? Can you see from this picture? Or is
So you can like stop it, right? Like stop the circuit. Cut the circuit.
Oh yeah, like where would you like to cut it?
Between the rings.
Oh yeah, like there's a little wire here.
In the
You mean here?
DC, in the DC one, you said that it's useless to.
Oh, the DC one. There's a gap, yeah. Oh yeah, because you don't want the current to jump.
You should control. Oh yeah.
Yeah. So you know it's the same idea here. You don't want those rings to touch because you want to force the current around into your resistor. If these rings touch, then the current will just jump from one ring to the other and not go through this resistor. So the reason for the gap between the rings is the same reason that there's a gap between the two halves.
The thing is between the magnet.
Yeah.
The same thing with the in DC motor.
Armature, yeah.
The same thing.
Same thing, yeah.
The current is flow then in that.
Well, we'll have to use a new rule because we last time used the left-hand rule to figure out the direction of the current.
Yeah.
It's a totally different rule for this situation.
Oh my god.
Yeah, you're never going to guess what it is. You'll never guess what it is. Go on, guess. What do you think it is?
Same.
No, it's not the left-hand rule. It's totally different. Exactly. How did you guess? Yeah. Well, what was your choice? It was left hand or?
We can think that the plane is same thing to like when you explain the plot.
No, we can't use the left-hand rule.
I mean just if you when you explain the plot, something like
Oh yeah,
boom,
yeah,
boom,
yeah,
boom.
yeah, yeah, yeah.
This is that.
Yeah. It's yeah, you're right. This is the magnetic field,
Huh?
and this is the plane. Yeah,
This
and
this plane is
yeah.
like
Yeah.
because this is designed like
so you really care about the Webers that cut the plane.
yeah.
Yeah. And you also care about the angle. So for example, when the plane's like this,
Yeah.
none of the magnetic field cuts the plane.
Like
And then
this.
when it's like this,
Like this.
it cuts it a lot.
Okay.
But really what's important here is actually how quickly it changes. So if the wheel is turning fast, it makes more voltage. Because of Faraday's law, the quicker the change in the flux per time, the more voltage there is. Yeah?
Do you repeat
About what?
when you vertical?
Oh yeah, so, well, I think that's, I'll repeat that when I go to the graph, because it'd be useful to have the graph. Can I go on?
It will matter which the way the circle goes which way.
Which way you turn it?
Yeah. It matters.
Yes, it does matter. But funny, because in the exam, they always turn it this way in the exam. Yes, interesting. If you're looking at it this way, clockwise, yeah. Can I go on? 'Cause I just want to draw the graph and then we'll finish for today.
Well, what's that black thing there?
Oh, that's just some resistor or whatever it is. Your bicycle light, if you like.
To draw this?
They could ask you to draw it, yes, or they could ask you to label parts of it.
I think I'm drawing.
It's only a few squares and circles.
3D.
What is the black one?
Oh, she just asked me that. A resistor.
Oh, I see.
No, resistor. I'm going to continue now. If you don't have the picture, you'll have to get on YouTube later. Continue it. So, finally for today. Okay. So, the coil, imagine it starts vertically. Okay, and we have do you remember we have the formula BA cos theta? Yes? Now what angle is cos theta measuring? It's the angle between what and what, if you remember.
This.
Yeah, between the normal. So if this is the plane vertically at the beginning, the normal is like this, perpendicular. Okay? And the magnetic field?
Same thing.
It's parallel to it.
Parallel.
So what's the theta?
0.
0. So what's cos theta?
1.
1. So you might think, hang on, Stephen, then that means it should be large at the beginning. It's like, no. The flux will be large. BA cos theta will be large. But it's not BA cos theta we care about, but what?
Change.
The change. So the change in BA cos theta, that's the derivative of BA cos theta, which is what?
0.
BA sine theta.
Yeah.
So what's sine of 0?
0.
0.
Yeah.
Yeah. So that's why when it's like this, there's actually no voltage. Even though the field is crossed and it's perpendicular, it's a lot of Webers.
Yeah.
But it's not, that's not what you care about. You care about how quickly it's changing. Now, listen carefully. Please, listen carefully and look at me. Right? Here's the plane. Here's the field. 4 fingers, 4 Webers. Okay? So it hits the plane, we have 4 Webers. Okay? It changes a little bit. We have 3 Webers maybe. So what is the change? The change is only 1 Weber. Quite small. Now, my plane is horizontal. How many Webers hit it now? 0, because it's parallel. It moves up a little bit, and maybe like 2 or 3 of them hit it. So the change is more dramatic. To go from 0 up a little bit, you could get like 4. That's much bigger than going from 4 to maybe 3.5. You know, that's why the voltage is 0 when it's vertical, because it's the change that matters, not how many Webers. Okay? In the exam, I've seen them ask students to draw this. They want the voltage and the positions of the generator underneath the voltage. So exactly this picture. Once you draw this, you can go.
This means voltage is occurs when the plane is rotating.
Yeah, the plane is rotating.
And should be rotated.
Oh, of course. Okay.
Steven,
Yes.
what is date for my
Oh, it doesn't matter. Just leave it. It's fine. You want to give that to me now?
This is not at point, it's just between the range.
Huh?
This is not at point.
Now, what are you talking about? This is the generator rotating,
Yeah.
and this is what the voltmeter measures.
Yeah.
So the voltmeter goes up, goes down, goes negative as it rotates.
Yeah.
This is rotating.
Yeah, yeah.
So what's confusing you?
Not confusing, just I'm trying to make it simple to understand easier.
I think it's simple enough. Did you draw this?
Yeah.
The voltages have limitation, right?
Limit, maximum, yeah.
Yeah.
Yeah?
Then the more speed, the more voltage is not correct.
Yeah. Yeah. If you turn the wheel faster,
Yeah.
you can get more voltage.
More voltage, but still have a limitation.
Yeah. But the limit is bigger.
we have assessment working?
Huh?
That's working on it.
Yes, assessments for tomorrow. Yeah. Okay, I'm closing this now.